Let's start. The first review is about the physical sciences. And you all know Newton's law, Hooke's law, and today we start from a simple example. You got the spring here, and they hang up a mass. Let's say this mass has the weight m, and the stiffness of this spring is k. And we're going to analyze the motion of this mass if we stretch a little bit, give the initial motion. So we all know Newton's law, the total force in here is the weight, which is mg, and it's right here. And the restoration force, we call it H, in Hooke's law, it's proportional to the k times x. Well, remember, when you use that formula, the x must set at the origin at the equilibrium point. The equilibrium point is the point if you don't apply any force, it's going to be stay still. And the other force you can also apply, you can put a little magnetic field, or you can do anything to make another external force. That depends on the question. What's Newton's law? The Newton's law says the total force equals m times the acceleration. But I put the little x, simple to tell you the acceleration is a double derivative of the position variable. The x is the position at the time t, and the origin is at an equilibrium point. You can have a choice, maybe downward is a positive direction. That's up to you. So in this case, we can see the acceleration times m equals this from the restoration force. A spring always like restore back into the equilibrium point. And that one is the weight. We put the negative here, then I'm wrong. The positive direction is this way, so we have the negative. And also, you have this, we call it a damping effect, or you just call it a resistance due to the air resistance. So we put all the x in one side, double derivative, single derivative, and the k, and then we put the g on the other side, and there's an m here, so mg. Now, there's a little tricky here. We talked about the equilibrium point. It really depends how you're going to choose. If you choose the equilibrium point without a weight, and then you need to consider the mg. But if you already consider the mg, literally balanced this spring, let that x equals 0 here, then you don't need to consider the mg because it's already canceled out from the little stretch of the spring. So if you choose the right origin, this is the balance between the stretch length and the weight. If you choose this point, as the origin, do a shift, and then you change the variable to y. What I'm saying is without this, maybe the balance is right here. That's the x equals 0. But if we put the weight, you don't make any motion. They're going to stay still at this point, x equals x0. And then now, you can drop off the weight because it cancels out with this stretch force. And then your equation will be a little easier. Without the inhomogeneous term, we get the second derivative for y. The y is simply shift a origin. And then by prime plus ky equals 0, and the mg dropped because it cancelled out this force. So we changed the inhomogeneous equation to homogeneous equation. But the problem is, here's not the first order. When you have the double derivative, you know what that means. It's a second order equation. So in this particular example, we will think about two different cases. The first case, we consider the mass stiffness of the coefficient k, but we neglect the air resistance. That means the B equals 0. And the second case, we consider the B small, not too big. We know it's air resistance. Okay, now, if the B equals 0, and make it easy, the m equal 1, the k equal 32. So we reduced this equation into only y double prime, b is 0, k is 32, equals 0. It cannot be easier than this for any spring mass system. Now the question is, we have not learned how to solve second order yet. The trick is pretty simple. We did last time actually by introduce the v equals the velocity of y, and then you get the actual equation. That's the additional equation here by you introduce a new variable. But now look at the v derivative is the double derivative of y, of course. Then you got this v prime equals negative 32y from here. So you got two first order. But the system ODE. So you reduce the order, but introduce one more variable. That's the trade-off. That's fine. And we assume you give a stretch of 1 unit of disposition to make it move. If you don't get any energy, they won't move. And start from rest. That means the velocity is 0. Then you coupled two initial condition. You remember this, we call it initial condition. So now you get a system, pretty simple. You know how to solve. We call this first order homogeneous linear system. Cannot be easier than that. And you can use eigenvalue to solve it, but that's not my concern. So all I concern at this stage is you get this system. And if you want, you can write it into matrix form. YV prime equals YV. You remember that's 0, 1, negative 32, 0. That's what you have. Now, let's consider the second case. the second case B is not 0, but pretty small. We let the B equal 1, or actually equal 2. Let it be equal to, come back to this symbolic equation. You got the 1, 2, 32, and now you got this homogeneous system. Equation, but it's a second order. What is only a little bit different, you need to introduce another variable v. Again, it's the y prime. And then you get this trivial equation. And the v prime is y double prime. Then you get the second equation, because y double prime equals this plus this. And now it's the v prime equals 32y minus 2v. And that's the second equation. And also you have the same initial condition. Then what we get, if you want, write into matrix form, it's going to be yv prime equals yv, and that's 0, 1, negative 32, negative 2. Not much different. And the only difference is you add this term because of the air resistance. Now, we use the stellar to simulate it. When you look at the stellar model, it's super easy. You got the two variables, then you got the two tanks. So here's the position, that's my y, and the velocity, that's my v. Look, what is on the pipe, on the switch. On that switch, you remember the derivative for position is velocity, then the change of position, which is specified here, is the velocity. We know the derivative of velocity is acceleration, then our change of the acceleration is here. So if we look at the equation, depends which one. If it's the first one, yv equals yv 0, 1, negative 32, 0, and you actually put this 1 here, v here, and put this. You see, this depends the acceleration, which is negative 32 of the y. Actually, see, the y is coming to here. That's it. That's done deal. The other one, when have the damping effect, the negative 2, the only difference is you need the minus 2v, and that's why you end up with this row. And the mass, we know equal 1. And what else we have? That's something else. K, that's negative 32. You can change. This is the reason we put it there. And the acceleration, what is this? Maybe some outside force. Well, we look at the simulation result. The two waves, the first one, the B equals 0, there's no damping. What that mean? That means in physical science, no damping, no energy loss. It's a constant transition of the is the potential energy to the kinetic energy. And the second one, when the B equal to, the energy is dissipating, and you get a little bit of rough curve like this of the amplitude, and this turned out to be this function.